Hi, so I'm going to be presenting the Panorama project. I thought it was the most interesting for me because it's a technology I always use, but I never fully understood the amount of engineering that went behind it. Um, so the problem can be stated as given a sequence of images with some percentage of overlap. Um, for this project, we said 30 to 50%. How can we stitch them together to generate one image? So as you see, we have like these three images. How can we put them together to get one image? So we start off by using the NMS algorithm, which stands for Adaptive Non-Maximal Suppression. We choose the best corners. We set it to 750. I found that 750 works great. Um, we compare all local maxima of the corners and choose the one with the lowest Euclidean distance. This reduces the number of points dramatically to only 750 strongest points. So then it helps with the choice of features later on. So as you can see, here is an output of the corners produced from the local maxima on the left. And after applying ANMS, we get way fewer points that are stronger corners because there were a lot of points in the sky, and these are not technically corners. Next, we produced feature descriptors, which has some encoding of the surrounding pixels. So for every corner, we took a 40 by 40 window, and just because some of the corners might be at the end of the images, so we had to pad the image using a replication technique. We then applied a Gaussian filter and then subsampled these windows to get a feature, 1 by 64 feature descriptor. Next, we feature matched these descriptors by comparing every feature descriptor with every other feature descriptor between two images. One challenge that I had seen was that when I had like 4 nested loops, the algorithm was running pretty slow. So vectorizing the sum of squared distances helped so much. Again, we had a cutoff of 0.8, and that cutoff was compared against the ratio of the two lowest sum of squared distances between the feature descriptors, and that was deemed to be a good match between both images. So here is the output. After matching, we see that most of the matches we have are actually pretty accurate for this image. Some of them are a little off, but once this is passed to RANSAC, it can remove all these outliers, which is the next step. Now, RANSAC is a great algorithm that we used a number of times during this class. Due to the nature of the algorithm with randomness, you have to set a high number of iterations. Anything in the order of thousands works great. The job of RANSAC was to find the best homography, which is a relation between two images. So we take a sample of points, 4 points, and then we estimate a homography using that, and then we apply it and see how far the new points are from the original points. We had a 5 pixel threshold, and we will look at the results right now. So this is after the removal of the outliers, and if we go back to the older image, we see that some of these like skewed lines are gone now, and we only pretty much all the points are actually correct. So if we map this point to this point, it's actually correct. This upper corner with here, they are actually perfect matches. And this is another example which should be deemed to be harder. And again, the matches are pretty accurate. This is another sample of a picture I took just to test that it actually works with different harder slash more natural images. Um, so we can even find some matchings with the clouds here, matchings with testudo. Okay, so the final step, which is warping. So we need to create a canvas to add all these images into one canvas. So we use the estimated homographies that was found from the previous step to find how big this canvas can be. So we already know the ends of the original images, so we just take the corners of those images, and then we apply the homography and see how far this image can extend. This also creates a lower and upper end for the axes. And one thing to note is that the base image, we had to apply an identity homography just so it can be plotted nicely on the canvas. And then there is a decision to be made in terms of how you apply the homographies to the images. So I found that placing the image in the center as the base and then applying everything from the left and the right to the base worked best because you don't get a lot of loss of information. Versus when you start at the left and you keep on applying and applying and applying, found that you lose a lot of information as you go on. So here is the 3 images warped onto the canvas, and this is before we blend them all together. And we used alpha blending to blend the images using the center weighing of the Euclidean transform. And this is the equation that we used to blend. Okay, just a quick explanation about what center weighing is. So this is the Euclidean distance transform. And then once you get your alpha, this is how the center looks like. And then once you blend them, you're obviously going to see a little bit of a seam here, but it's way less than other techniques. Yeah, and this is my result for a couple of sets. We can scroll through them. We obviously see a little bit of like the seam is not really well blended here, and that can be improved by better techniques of alpha blending, like Laplacian blend, which is something that I was looking into. And again, there's a little bit of a seam. You could also like crop the image at the top to make it look more natural. These are pictures that I took with my own personal camera. There's again with here it was actually a problem with estimating the homography, so we can see that the line here is pretty much straight, but as we go towards the end it starts to fade off. Yes, same. Yeah, that's pretty much it. Thank you so much.